Astronomers tracking 3I Atlas say it has altered its course, worrying scientists about its close proximity to Earth.
In fact, I do think that, in the past we worried about existential threats from artificial intelligence, from the change of the climate, or from an asteroid that will impact the Earth. But there is another item that we should add to the list. Seem to be some teardrop shape to the plume of gas and dust around it. It's just not clear what this object is. A cloud of gas around it that is mostly carbon dioxide. It raises the question of whether this is a typical comet, a natural object, or maybe something technological.
The vastness of interstellar space conceals countless enigmas. On rare occasions, the cosmos delivers us a visitor, a phenomenon that transcends mere astronomical curiosity. On July 1st, 2025, using the NASA-funded Atlas Survey Telescope, astronomers glimpsed something extraordinary, an object from beyond our solar system, moving not at a leisurely pace, but at nearly twice the speed of any previous interstellar visitor. This object, now catalogued as 3I Atlas, swiftly joined a select group, only the third such interstellar object ever confirmed after ʻOumuamua 2017 and Borisov 2019. Each of these traversing bodies has posed new questions about the universe's workings and the nature of objects that roam between stars. But 3I Atlas, racing through our solar system, has already confounded expectations, challenging astronomers with unprecedented features that may expand the boundaries of our knowledge. August 27, 2025, the Hubble Space Telescope obtained the sharpest image yet of 3I Atlas. Far from a distant point of light, the image resolved both the nucleus, remarkably allowing an estimate of its size, and a newly revealed tail extending behind it. This tail, reminiscent of the familiar trains left by solar system comets, appeared with characteristics that sparked further questions. Its shape, coherence, and behavior upended familiar ideas of how comets behave when entering a stellar system. A tail, unlike any other. To appreciate the import of these findings, consider what astronomers ordinarily expect. Comets, whether native to our solar system or visitors from beyond, develop their characteristic tails as solar radiation warms their icy nuclei. This causes volatile materials to sublimate, releasing dust and gas to form a tail stretching away from the sun under the influence of solar wind. 3I Atlas, however, presented peculiarities. The Hubble Space Telescope's unprecedented image did not just show the nucleus, but a tail of surprising clarity and uniqueness. Unlike the diffuse, chaotic tails typical of solar system comets, this one was crisp and seemingly structured. The material did not scatter as quickly nor swirl as expected for dust ejected by solar heating. Instead, the tail appeared more coherent and directional. This was paired with the object's striking velocity. 3I Atlas moves through our solar neighborhood at nearly twice the speed of previous interstellar comets. Such speed, coupled with the persistence and alignment of the tail, challenged basic models of cometary behavior. Spectral analysis also suggested deviations from ordinary expectations. The chemical composition of the tail did not align perfectly with the typical fingerprints of water and carbon-based ices known to dominate solar system comets. Instead, astronomers detected hints that the material might have been altered by cosmic rays during its long voyage through interstellar space, resulting in compounds not commonly observed in local comets. Are these effects consequences of the void, signatures of physics unique to the interstellar medium, or are we observing characteristics of pristine material shaped beyond our solar system, now reacting anew under the influence of our sun? When tails don't behave, let's step back. Before 3I Atlas, only two interstellar objects were confirmed, ʻOumuamua and Borisov. Each recalibrated astronomers' expectations. ʻOumuamua, elongated and tumbling, showed no observable tail, leading to debate over possible outgassing or non-gravitational forces at play. Borisov, meanwhile, resembled a more typical comet, dust and gas behaving as theory predicted. Now 3I Atlas, with its sharply defined tail and extraordinary velocity, again redefines possibilities. The Hubble images from August 27, 2025 are striking not just by their clarity, but by what that clarity reveals, a tale that blurs the distinction between the passive effect of solar heating and something more actively maintained. The tail's coherence and persistent alignment, even as it whips through the solar wind at record speed, raised the possibility that previously unrecognized processes may be in play. Furthermore, the tail's angle relative to the sun's rays did not always match predictions from standard solar system comet behavior. Such deviations have prompted astronomers to carefully reconsider the assumptions behind conventional comet-tail dynamics for objects originating beyond our sun's influence. The fastest comet ever observed. Much of the curiosity surrounding 3I Atlas stems from its remarkable velocity. Detected on July 1, 2025, its approach speed was nearly twice that of previous interstellar objects. In astronomy, speed is a chronicle of an object's past. A visitor moving this fast must have been accelerated by intense gravitational encounters, perhaps with one or more stars in its home system. Compared to comets born in our own Oort cloud or Kuiper belt, interstellar visitors already stand out. But Borisov, until now the fastest, was left behind by 3I Atlas's astonishing pace. Calculations suggest that only powerful, ancient gravitational interactions, perhaps with multiple stars, could have imparted this much momentum. Its origin story, therefore, speaks of eons spent in deep space, battered by cosmic rays, not just a recent ejection. Detailed observations of its nucleus by Hubble show it to be robust, likely possessing unique chemical or physical properties resulting from its interstellar sojourn. Durability at such velocities is not common. Most cometary bodies would fragment under similar stress. This observation hints at material and structural secrets shaped over unmeasurable stretches of time and distance. As intriguing as the nucleus may be, it is the tail, the object's interaction with our local space, that carries the greatest mystery. Imaging the unknown. The August 27, 2025 Hubble image stands as a milestone. No previous observation has so finely resolved the features of an interstellar object. For the first time, scientists could directly estimate the size of the nucleus, placing it at an estimated 740 meters in diameter, perhaps slightly larger than Borisov. The density implied by the observation supports theories that the comet spent most of its history far from any star, forged and altered by the constant bombardment of high-energy particles across millennia. Around this dense core, a visible sheath, evidence of interactions with the solar environment, emerges. Most striking of all, however, is the tail, which grew increasingly visible over weeks of observation. Both from a single image and in series, the tail's behavior defied simple explanation. Its brightness, persistence, and orientation were not consistent with what solar wind alone could explain. While solar heating certainly contributed to outgassing, the behavior of the resulting plume refused to match the established models. Animation built from multiple observations reveals further irregularity. The tail's length changed at a rate not easily predicted, sometimes shifting direction in response, not just to the sun's radiation pressure, but perhaps internal or previously unrecognized mechanisms. At nearly double the velocity of previous interstellar comets, dust and gas ejected into the tail should disperse rapidly, yet the tail remains coherent. Comet or propulsion? The striking qualities of 3I Atlas's tail have led to lively debates in the astronomical community. The word propulsion gets raised not in the sense of artificial or engineered thrust, but as a metaphor for the coherent, directional way in which the tail appears to be maintained, even in defiance of the dispersal expected at such velocity. To be scientifically cautious, no evidence supports artificial propulsion or the presence of intelligent engineering. The context makes clear this is a natural phenomenon, but one that challenges the boundary between passive outgassing and processes that could, in effect, impart some momentum or directionality to the ejected material. Some models suggest that in interstellar space, cumulative cosmic ray bombardment might alter a comet's chemistry, allowing for the buildup of gases that could vent in a more focused, perhaps even sustained fashion, producing plumes that are sharper and more persistent than the diffuse clouds seen in ordinary comets. Such theoretical processes remain under study and cannot be unequivocally asserted. What is clear is that compared to Borisov's more familiar trailing gases and dust, and ʻOumuamua's lack of any visible tail, 3I Atlas presents a compelling contrast. Evidence in context. These extraordinary findings demand the highest standard of evidence. Ongoing work by NASA and other international teams is scrutinizing the data, comparing images, spectra, and light curves. Every anomaly is carefully recorded, every divergence from expectation weighed. As more images emerge, including those from the sharp-eyed Hubble Space Telescope, the record grows. The tail maintains its structure, its emission and alignment continue to surprise. Its chemical signatures confirm the object's status as a comet, but refuse easy comparison to known types. The Atlas survey's initial detection on July 1, 2025, prompted immediate follow-up, enabling more detailed study than for any prior interstellar body. Each new, crisp Hubble image, especially that from August 27, 2025, confirmed the persistence and nature of the tail, while sharpening debates over its source and survival in our solar system's environment. Astronomers are exploring new methodologies for studying such objects, seeking to analyze isotope ratios in ejected material, or using sensitive instruments to assess the interaction between the nucleus, its emitted gases, and the solar environment. These emerging lines of study, sparked by the peculiarities of 3I Atlas, could transform our understanding of cometary bodies, both local and interstellar. The ongoing mystery. What stands beyond dispute is that 3I Atlas is a record breaker, our solar system's fastest recorded comet and only the third confirmed interstellar wanderer, following ʻOumuamua and Borisov. Its discovery and subsequent examination have forced ongoing revisions to our knowledge of both cometary behavior and the broader spectrum of objects populating the galaxy. Unlike the Oort cloud and Kuiper belt bodies, which drift in stately patterns defined in the deep past of our solar system, interstellar comets are visitors from environments shaped by entirely different histories. Borisov, for all its velocity and ambiguity, behaved as models predicted. ʻOumuamua, the pathbreaker, had its own set of mysteries. Now, with 3I Atlas, astronomers face features they cannot readily explain, especially in the anomalous form and persistence of the comet's tail. What does this strange, sharp tail tell us? Is its chemistry a relic of eons spent exposed to deep space radiation? Is its structure evidence of processes more energetic or sustained than anything yet witnessed in our own comets? Or are we simply encountering, for the first time in detail, the vast diversity that defines the universe's wandering ice and rock fragments? No immediate answers present themselves. The world's leading astronomical teams pour resources into studying every fragment of light. Models of comet-tail formation are revised, tested, and challenged. The consistency, directionality, and resilience of 3I Atlas's tail stand as continuing puzzles, signaling that the mechanics themselves may be more complex or more variable in interstellar contexts than previously believed. A new frontier for exploration. The arrival of 3I Atlas underscores how much remains to be discovered. Scientific interest in the study of interstellar objects is at an all-time high. Proposals for new rapid response missions, ranging from nimble CubeSats to more ambitious probe concepts, are under discussion, with the aim of intercepting and sampling such objects during their brief, precious visits. This is no simple feat. The speed and rarity of these visitors demand extraordinary planning and responsiveness. Meanwhile, advances in telescope technology and data analysis will enable astronomers to detect more objects like 3I Atlas earlier, giving giving the community more time to mount coordinated observation campaigns, from high-resolution imaging to detailed spectroscopic analysis. Each new visitor offers an unparalleled window into material and physical processes untouched by our sun's history. The tale of 3I Atlas, with its persistent structure, unique composition, and defiant orientation, has become more than an astronomical curiosity. It stands as a challenge, a sign that however much we have learned of comets in the sun's neighborhood, the universe still has the power to surprise. Implications for cosmic discovery. The scientific implications ripple outward. If interstellar comets can exhibit such persistent, structured, and chemically unusual tails, what else might be encountered in the darkness between stars? Each new interstellar object may provide information on the composition, environment, and processes of distant planetary systems, places that, until recently, existed only as assumptions in our models. Astronomy is no stranger to paradigm shifts. The detection of Oumuamua in 2017 sparked the era of interstellar object observation. Borisov affirmed the existence of more familiar cometary visitors from afar. Now, 3D Atlas, with its speed, unique tail, and puzzling chemistry, may signal yet a further transformation, one in which the differences between comets are as instructive as the similarities. Some researchers speculate that violent environments, stellar storms, supernovae shockwaves, or other energetic mechanisms could imprint themselves on these bodies before they even enter our solar system. If so, every aspect of an interstellar visitor's structure, from its nucleus to its tail, is potentially a record of the physical conditions it survived. Every passing comet, therefore, might represent a time capsule from a different era in a different star's domain. Such speculation is grounding itself now in observation, not conjecture. As data build and interpretations expand, astronomers will refine their understanding, moving from questions to evidence-driven conclusions. Looking toward the unknown. As Comet 3I Atlas hurtles through our solar system, its secrets unfold incrementally. Each observation, each new data point brings science one step closer to understanding the processes that shaped it, and by extension, the broader mechanisms that govern matter in the interstellar medium. Confirming only 3 interstellar objects to date, the astronomy community is acutely aware of how much remains unknown. However, the nature of 3I Atlas's tail, its defiant persistence, sharp structure, and unusual chemistry underscores the dramatic possibilities confronting us as our observation capabilities improve. In the coming years, more visitors will likely be found. Some will be more familiar, echoing the expected forms and behaviors of local comets. Others may, like 3I Atlas, challenge everything we thought we knew about the deep, cold spaces between the stars. For now, 3I Atlas stands as both question and answer, a sample of the cosmos larger and stranger than any one system. Its tail, cutting through the solar wind, inscribes on our night sky a sweeping lesson. Every interstellar visitor brings with it not just dust and gas, but profound questions about our place in the universe and the physics that shape it. The frontier of interstellar exploration is only just beginning. Every new visitor offers the hope not only of discovery, but of understanding, the kind of understanding that arises when curiosity propels humans to peer deeper, ask more precise questions, and rigorously test the surprising answers that nature offers. As we track the continuing path of 3I Atlas, let us remain alert to the lessons, expected and not, that it brings. The cosmos holds more surprises. The more we learn from today's mysteries, the better prepared we'll be for tomorrow's. Keep watching the skies and let your curiosity lead you. For in each new comet, every unexplained feature, and every surprising turn, the universe extends an invitation to question further, to seek understanding, and to embrace the wondrous complexities of everything beyond our world.